Let's look at this exercise 8, 1.1.3. So this exercise is about a particular example of chain complex vector spaces. So the exercise is here to show that any chain complex vector space is isomorphic to chain complexes vector space of the following type, which is say n equals bn dx sum hn dx sum bn minus 1, and then say your dn, and then we have your bn minus 1 hn minus 1 bn minus 2, etc. And so what we have to show is that suppose you have arbitrary chain complex vector spaces, and then you have to construct a morphism of chain complexes such that it is isomorphism of chain complex. So by definition mean that you're able to also construct the inverse morphism such that the constructed two morphisms are inverse to each other, which means the composition is the identity morphism of chain complexes. This is more restrictive than quasi-isomorphism. This actually is identity on each level. So let's see, how could this be the case? So I'm going to define what is Bn. Once I define what is Bn, I then have to define what is Hn, and then I constructed this, and then I'm going to construct a morphism. Okay, the observation is that if you have element through Dn, this is mapped to by the construction Z 0, 0, and so the kernel is this part. This is the intuition. So I'm going to define Bn plus 1 to be the direct surrogate of Cn, such that Cn is isomorphic to Bn minus 1 direct sum with kernel of Dnc. Right, and then notice that H say n is isomorphic to, HNC is isomorphic to kernel of Dnc quotient by image of Dn plus 1c. So this is subvector space of Cn. This is also subvector space of Cn, and so actually this is isomorphic to, again, subvector space of Cn. Okay. In other words, actually, what do we have? Kernel Dnc is actually isomorphic to image Dn plus 1c direct sum with H, because everything is vector space. That's very nice. You can always take the experiment because you can always form a basis starting from a basis of any subvector space. And so basically this is kernel Dn, and kernel Dn could be further written as image of Dn plus 1 plus Hn. And this is kernel Dn. Sorry, this is the experiment of this two. Okay, so in other words, you could define differently. You could say that you could define Bn to be a image or image of Dn, right? Should be the same as the experiment of kernel DNC. Basically, it's because you also have Cn quotient by kernel of DNC isomorphic to image of DNC. So this tells you that Cn is also isomorphic to kernel DNC. Their sum with image DNC. And we're just claiming that. We just define this is our Bn minus 1. It is the image of Dn, and it's also the experiment of kernel DNC. And it's just we are rewriting this kernel DNC further as Hn direct sum with image Dn plus 1c, which is Bn. Okay, so anyway, we have defined a complex. It's easy to check. This is complex simply because you just compute this composition twice, give you 0. And now let's check this commuted diagram. Basically, we're using, let's do this. Any Cn could be written as the sum of kernel and image, and you can further retain it as image Hn, image sum Hn, and with image of DNC. If you rewrite it that way, then it will just be alpha, beta, gamma. I suppose gamma, alpha is in, it could be written uniquely, written as alpha, beta, gamma, where alpha is in image of Dn plus 1c, and gamma is through this isomorphism. Or into the subspace which is isomorphic to the image of DNC. And so this map is just gamma plus 0 plus 0, and when you map it down, you just map it alpha plus beta plus gamma. Similarly, this is gamma plus 0 plus 0. Obviously, this can be diagram, and the inverse map is the same. Actually, what do we have defined? This is just identity map in some sense. After isomorphism, of course. So U is an isomorphism. If you want, you can call this UN. Let's just pick an example. Let me just pick an example. For example, if I pick P2, and this is differential. P2 I mean polynomial of, let's just say P1. Polynomial is one variable, degree 1. Let's call it P1, and then it's just differentiation. This is just map to A1, and then further map to 0. Derivative of polynomial, okay? And so in this case, the basis of Pn is just by 1 and t. And so how am I going to define, say this is my Cn, how am I going to define my Bn minus 1? My Bn minus 1 will define to be the kernel, to be the image of Dn plus 1. The image of Dn plus 1 would just be the span of 1. Okay. And in this case, what you write would be Pn is isomorphic to Bn minus 1, their sum with kernel Hn minus 1, their sum with Bn Hn Bn minus 1. So this should be the image of Dn. And we still span 1. And in this case, the kernel quotient image is obviously the kernel should be kernel is, let me write here. Let's repeat this example here. Here's this derivative. Let's call this Cn and call this Cn plus 1, Cn minus 1, and minus 2. So in this case, I first compute the homology group to the kernel of Dn. is just kernel dn is 0 plus a1 polynomial such that a1 equals 0, and so it's just the span of identity. While what is the image of the n yes, it is all the a1 in, let's say, for example, real polynomial. But when you talk about this P1 quotient by the kernel of Dn is isomorphic to the image of Dn, and we realize Pn written as a sum of kernels Dn isomorphic with the image of Dn. What do you see? Yeah, the image of Dn is isomorphic to the span of T. This as a submodule of P1. Actually, what you say here is kernel of Dn plus sum with span of T. And in this example, the Hn are all isomorphic to 0, right? Because each kernel Dn equals image Dn plus 1. Isomorphic Dn plus 1. And this is saying that this is, so the direct experiment of Kn by our construction before this is called the Bn minus 1. And so this is actually Bn, and actually you can rewrite it as direct sum with 0. This is our Hn. And so this is saying that any element here could be written as a0 direct sum with a1t or direct sum with 0, or if we keep the order of previous example, it should be this. And then this is mapped to a0 plus 0 plus a1t. And this is mapped to a1, although as isomorphism, vector space is isomorphic to a1t. If you fix the basis, you can take care of the coordinate, and it will be of the form just like this, right? Take this example just to show this little tricky thing, which is about a priori the image. The image is not subspace of the domain, but for vector space is isomorphic to a subspace of the domain, so it could be written as the experiment. The experiment of this domain vector space.